So one more thing I want to show you about those Navier-Stokes equations, even in their differential form, is this somewhat magic way that you can analyze super complex things that always has amazed me in my graduate research I've done, that it just ends up working. So I just want to show you where the Reynolds number really comes from in the analysis. So we write what we had before. The gradient of pressure and then the curvature of velocity. That's how I think about those terms. So recall that, right? This differential operator is actually it's a vector of operators, right? So we have, if you remember, it was this in Cartesian, right? So if you dot it, you're going to sum up terms, like in this term right here. I'm describing this thing as, again, the vector like this. So this is called the Laplacian, and it's actually this dotted with itself. So it's actually a sum of terms, not a vector. So, right, so this is a sum of terms, so then it will operate on this each time. So one thing is, if you do have that cube that we're always drawing, right, where all of these terms, right, they're all equal. So we have the z, x, y. So if you think about just a small little cube, and you say that all of these dimensions are the same because it's a cube, they're equal, you make these substitutions into the operator saying, well, they behave like, right, a 1 over that dimension. So you just make a little similarity look, a little sign. So you say, everywhere I see one of these things, I'm just gonna, it's just gonna behave like a 1 over d, where d is the length, width, or height of that cube that you have. Likewise, and where we see this term, we're going to say, well, that's going to look like 1 over d squared, or d is the length, width, height of the cube. And it's just magical stuff, but it's the best way you can analyze things like this. So we're just going to make these substitutions to turn this large partial differential equation into just an algebraic statement that we can work with. And we're just going to substitute these scales into the equation. So that stays the same. This time operator, I'm going to say, is just a certain time. You can think of it as a frequency too. So let's say the time scale, if you're looking at time scale of the globe, really you're looking at like per month. So the time scales in days. For microflows, we look at like milliseconds. So this term can just be some digit that you prescribe. And then this one will just say some characteristic flow or some measurement, right? Some mean measure of velocity that we seem to have. So this term, which was a differential term, now just turns into this algebraic statement of variables. I have 2 of these here. So that looks like that, still here. And now, right, anywhere I saw the little triangle, I just turn it into a reference dimension. And then you make this little scale term. I'm going to call some reference pressure, and then anywhere I saw that. You don't even need to keep your negative signs when you do this, but sometimes it's confusing, so I'll just keep everything around. Same stays the same. Boom. And it's squared because the Laplacian had 2 length scales under it, so it's going to behave like this. You could actually do all this, and right, some people might say, why didn't you rate this as 3 over d? Because I said, right, if these all just turn into a 1 over d relationship, why aren't you saying 3 divided by d squared? Well, you can still do that, but it won't really matter when you just get to this fundamental little observation, right? So this is your unsteady term. Okay, this is the call it the inertial term commonly. Here's your pressure force. And then here's this the viscous force. So you can see these clear sort of four terms that are playing a balance in which one of these terms matters and which one of them do not matter. So, right, remember the Reynolds number, we always say to ourselves the Reynolds number is the ratio of inertial to viscous forces or time scales or however you want to rationalize it. But we know it's a ratio of viscosity and inertial. So with that being said, if we're looking at a ratio, let's just take the ratio of this. So this is my inertial term, and I'll divide out, right? And I'll just divide the entire statement by that, right? And there's order 1 concepts that come up, or whatever you scale, but don't worry about that. So I'm just going to divide the whole thing, which is multiplying by the inverse, right? And what I've done is I'm dividing out I'm dividing the inertia term with the viscous term. So after you do this, right, you'll have over here the U naught T. This just becomes 1. This will become and there it is. See, this is really, so right, you see it for measure, right? You see when we're going to compare this viscous term to this inertial term, and we're just going to divide this out to see what size and what number we have, right? You're going to have this thing right here. So that's really 1 over. Right? So now you can kind of see, right, this whole concept of large or small Reynolds numbers. If the Reynolds number is very, very small, so sometimes people will say Reynolds number much, much less than 1. You having 1, think about taking 1, dividing it by like a very, very small number. Though this term then explodes and becomes very important. So that's where you have this viscous term mattering most, because this is sort of the scale in front of the differential operator. And then the other case is if it's really, really, let's say, big like that, you notice that this term, right, think about 1 over 10,000. That means that this number, right, it goes away, right? So then that term is not there, and then you get this balance of the pressure and the inertia. So those are the 2 cases, and it just comes from taking that Navier-Stokes equations, and you make these wildly magical statements on scale, but then you can describe something like this. And that's where the Reynolds number that we're tackling all the time comes from. It's from Navier-Stokes. It measures the viscous term to the inertial term. But I always thought it's cool to just kind of see it happen. So hope that helped.